Thank you for attending, and thanks to DDD Europe for inviting me. So I'm talking today about the language of actors. And last year when I spoke at DDD Europe, I touched just a little bit on the use of actors in a domain-driven design model. And after my presentation, one of the attendees or a couple of the attendees approached me and asked, you talked about not chasing shiny objects in your development, and then you present this brief introduction to using the actor model with domain-driven design. How do you reconcile that with not chasing shiny objects? Well, I hope to address that in this talk, along with what some of the advantages are to using domain-driven design. If you'd like to get in contact with me, this is a way to do so. And just to show you that these are my three books, this talk is sort of an intersection of these. So domain-driven design with reactive messaging with the actor model. So I think you're all familiar with this approach to software development, objects. Maybe not all of you are currently using objects, but I think most of you have used objects. And this is a fairly typical pattern where one object sends a request to another object. This is a client object talking to a server object. Now, this doesn't mean a server as in an application server or a web server, or it's just an object and it provides a service. So I think in the parlance of Rebecca Werfsbrock and her discussions about responsibility-driven design, this is what I'm talking about: a server object that takes a request from a client object. And most notably, when this client makes a request, what's it going to do? It's going to do nothing, because it's blocking until the server fulfills the request. And it could be that that server object is using other server objects and other server objects. And so this original client is blocked potentially for a considerable period of time with regard to a specific use case that the user or some other system is executing. So because objects block, and because of this trend, and I start from the year 1973 and go through 2003 on this chart for a specific reason, and I'll tell you why 1973 is a significant year to this chart. But as you can see, from around 1973 to around the year 2003, 30 years, software was able to take advantage of the ever-increasing power of the microprocessor. And I'm talking about both clock speed and transistors. And so there was a lot of payoff in upgrading every year and a half or 2 years in your hardware, because you could benefit, your software could benefit from this ever-increasing power. And for people who, developers who were writing software back in the day where these kinds of great power curves were increasing the speed of software, and when they didn't know how to properly write software that was subject to the speed of a machine, you may remember back to the days like I do, where suddenly things that used to have a built-in delay in the software would suddenly not work anymore, because the delay was built on a loop, an empty loop that just counted from 0 to a million or whatever, and because on an 8088 processor, this took 3 seconds, now if you're running a 286 processor, it takes half a second or less, and so the software started breaking. Well, that's the kind of increases in power that we were experiencing back then. And this trend continued. It's called Moore's Law, right? And this trend continued up until about 2003. Now notice that on sort of the left-hand side of this grid, or the top arrow, shows that the number of transistors that were added to microprocessors continued to grow, and I believe it still continues to grow. But in 2003, something dramatic happened, and the actual clock speed of processors started to fall off. And there are various reasons for that, one of them being that they actually can't find a good way to cool the processor enough to allow it to run at a faster speed, so there's no practical way to keep the processor cool enough to allow it to run hotter and hotter. There are other reasons for this, but this has a significant influence on where we are going today. So to some extent, we can be like that actor face that's all sad-faced, right? Because, oh, the clock speeds have fallen off. But the reason that we have to be jubilant like the other actors smiling is because in response to that, instead of making processors faster, the hardware engineers started adding more processors, more cores. Yay. That has had a big influence, and cores matter. And just to give you an idea about the number of cores available, just my Mac that I'm running here has 8 cores running on it. This is just a typical MacBook Pro. And commodity servers have at least that many cores on them these days, but cores are increasing in number. However, the cores themselves are not getting faster. Okay, so we have these cores. What do we do with them? How do you take advantage of these cores? Because a core actually that supports hyperthreading can run 2 threads at a time. So if you have 4 cores with hyperthreading, you can run 8 threads at one time. But the problem is, threading is hard. Have you written real, true multi-threading code? Is it right? You may be one of the few people who can confidently answer that question. Yes, it's correct. Because the actual assertion among multi-threading experts is that most multi-threading code is wrong. So even if you think your multi-threading code is right, are you really, really sure? Sometimes you can't even see the problems that happen. But let's take this thought a step further and say, you know what? Actually, multi-threading is easy. I can create a simple work queue. I can feed new tasks into the work queue. So I'll use thread 1 to put new tasks on this work queue, and I'll use 3 other threads as worker or task execution threads, and they're going to read the tasks off of the work queue, and they're going to, in a multi-threaded way, asynchronously, concurrently, carry out these tasks. So actually, I can design a really easy-to-use multi-threading approach. The problem is, even with this, is depending on the implementation that you use, and because there are multiple accessors to this work queue, do you introduce synchronization or blocking in order for the thread 1 that's adding work or tasks to the queue so that it can have independent access to the queue. And then, because thread 2 and 3 are trying to get work tasks at the same time, are they being blocked because the work queue is temporarily busy or locked? And then it looks like at this moment in time what we actually have is a situation where thread 4 is running, but thread 1, 2, and 3 are blocked. Then thread 2 and thread 3 in some order are able to finally access their work items, but the work items that they access are overlapping in that they're both using the same entity or working on carrying out a task on the same entity, and because of that, the entity blocks. So thread 2 or thread 3 has to wait for the conclusion of the other thread's work or task on this entity, and then it can move forward. So even if you get multi-threading right, it's not untypical for a multi-threaded application or subsystem to actually block a lot of the time, essentially turning this multi-core system or these multi-core systems that we can take advantage of into single-threaded servers. So multi-threading is hard no matter what. Now, I admit you could take a different approach on this. You could say that this work queue with tasks being put into it could follow the disruptor pattern, right? It could implement the disruptor pattern, but that would mean that you have a single writer and a single reader, which maybe that doesn't fit your use case. So while single writer principle might benefit some use cases, it may not, in this circumstance, benefit your particular use cases. So what can we do about this situation? Well, there's the actor model. The actor model is message-driven. And the actor model works by one actor, in this case, the sender. You could call this the client. The sender knows the address of the receiver, and therefore it can send a message to the receiver. A bit earlier, Mel Conway was talking about the Smalltalk language, and I was really happy to hear that Mel Conway loves Smalltalk even still today. I do too. Smalltalk was built on message sending. However, Smalltalk originally was built on synchronous message sending. So it was much the same that we think about a method invocation today, but the real message paradigm was originally one object sending a message to another object, and that message had what was called a message selector, the name of the message, and that message selector would look up in a dictionary the method that was going to act on that message or was mapped to that message invocation or send, and that method would then be invoked, but in the background. So that was the dispatching behind Smalltalk. And then someone else took this one step further, and I'm going to talk about that in a moment. But in essence, if you will, think of this sender and think of the receiver as objects. And they're probably even more true to the object paradigm, the original message, the original intent of using objects than most objects are today. That is because the actor model is based on messages. And Alan Kay, the inventor of the Smalltalk language, said that the big idea behind the object paradigm in the first place was message sending. And I'm going to drill down on this further. But essentially, to sort of get your mind in gear for this presentation, the rest of this presentation, think of sender as an object, think of receiver as an object, But the message that's being sent to the receiver is sent to the receiver asynchronously. That means that the sender does not block while the receiver is handling that message. But they are still essentially objects. Okay, is the actor model itself just a shiny object? Is it, am I out of place in saying, don't chase after shiny objects, and and yet I'm presenting something that's relatively unfamiliar to a lot of people? Actually, the reason that I presented the year 1973 before is because that is when the actor model came into existence. So just a little history about the way objects came about is the Simula programming language was getting traction. I think it was around 1967, 1968. And then Alan Kay took note of some of the work in Simula, plus other influences that he had, and from the, I think, at least early 60s on his development career. And Alan Kay then came up with the idea of Smalltalk. And there was originally a Smalltalk 71, so 1971, and then there was a Smalltalk 72. And Carl Hewitt, a professor at MIT at the time, somehow got his hands on Smalltalk 72. Now, I think the broader public didn't really know about Smalltalk, or maybe had heard about it but couldn't use it until about the year 1980 with Smalltalk 80. But Carl Hewitt got his hands on Smalltalk in 1972, and the message sending between objects inspired Carl Hewitt to come up with the idea of actor model. And he worked with a few other people, but he's widely regarded as the inventor, at least maybe primary inventor of the actor model. However, at the time, remember that grid that I showed you before of the way processors were working at the time. If we go back to 1973, this is what we're talking about. Clock speeds on processors weren't even running at 1 megahertz at the time, and there were about 4,000 to 5,000 transistors in those days. Now there are tens of thousands, or tens of millions, I'm sorry, or what, maybe even tens of billions, I can't remember, transistors now. So to give you an idea, this is the world of Carl Hewitt when he is discovering this approach to computing that he called actor model. But what he envisioned were these great, highly scaled, networked server systems that were, in essence, multi-core and had high-speed networking between them. So Carl Hewitt was way, way, way ahead of the curve, way ahead of his time, because it wasn't until a few decades later where the actor model even had any impact at all on the industry. But this is the story of where actors come from. And actors are reactive. So if you're keeping it up with, or want to keep up with the reactive software development and reactive systems community, there's a website called reactivemanifesto.org, and you can read more about reactive there. But essentially, reactive is software that's responsive, elastic, resilient, and message-driven. And it's really the message-driven aspect that allows for these other three characteristics of actor systems. So we could focus on responsive, sub 25 millisecond response times in a service is not out of the ordinary when using the actor model. Elastic, so you can grow and shrink these graphs of systems. It's resilient in that this is an interesting aspect of the actor model, is that a client who interacts with an actor, so a client who sends a message to an actor, if that actor fails before, during that request, before or during that request, the client doesn't have to deal with the crash. It's the parent of the actor that deals with the crash. So, sorry, got ahead of myself. So the resiliency of an actor system is much greater because the component that is in the best position to care for an error situation of another actor is the one who cares for it. It's the parent or maybe the grandparent or someone, some actor in the hierarchy of parenthood of the crashing actor takes care of this situation, and they can stop the actor, they can stop an entire hierarchy of actors, and there's a lot of things that they can do. But again, what ties all these together is being message-driven and asynchronous messaging. So why actor model now? Why is the actor model a thing today when in 1973, and even until maybe the mid-'80s, no one was paying attention to the actor model really much at all? Well, it's because of things like, the fact that memory is so inexpensive, that the cloud is upon us, that we have small devices like mobile phones, and everybody has at least one phone, and the fact that disk space is cheap, and we're headed toward the Internet of Things, which is predicted to be, this gigantic market in around software and hardware development within the next several years. So, and all of these things are more affordable, and the network is faster. So, because cores are essential to running the actor model in an efficient way, and the Intel Xeon processor can have up to 88 cores standalone, and if you put co-processors together of the Xeon Phi, you can actually get 200 plus cores. And so you can imagine the power behind simultaneously running 88 or 200 things at a time. Another good reason to consider the actor model is that we should embrace latency and we should embrace network failure. And when we rely on synchronous communication, as in RPC or even RESTful invocations, RESTful requests on servers, those requests can go unfulfilled because of crash or timeout. And so when you introduce messaging into your systems, you're introducing latency as a key design element. And so latency becomes, part of the design of the software. And so when you experience latency, you don't, fall off a cliff because, oh no, I didn't get a response to my request. Another an important thing to consider is that you can do more with the actor model using less system resources. So sometimes, people use the argument or the concern of, well, I'm not, Amazon scale. I'm not Netflix scale. We have a relatively small system. Do we really need the actor model? Well, just to give you an example, there's a practical case study of an organization that was required somewhere in the number of 80 servers to run their processes, but when they switched to reactive systems with the actor model, they were able to scale that down on a permanent basis to about 5 servers. So imagine how much savings that is if you are hosted in the cloud, and even just to the cognitive overload of dealing with all the infrastructure of 80 or hundreds of servers when you could do much more with much less. So again, the premise behind actor model is direct asynchronous messaging. And I want to key in on the word direct here, because sometimes people will loosely use the term actor model and actors to describe asynchronous messaging in general. For example, maybe you have a middleware messaging mechanism, like based on JMS or MSMQ or whatever it happens to be, and you're able to publish messages to subscribers. And you might refer to that as actor model. Technically speaking, that is an actor model because the publisher of the message doesn't have much idea, if any at all, of the subscribers to those messages. Even if you are using a message queue, just a single queue, you can still have multiple listeners on the receiving side of the queue, and therefore, technically speaking, you are not one actor sending a message directly to another actor. Actor model is, in fact, direct asynchronous messaging because the sender of the message must know the address of the actor that it is sending a message to, and that message is delivered asynchronously and processed asynchronously. Actors are also lock-free, share nothing. These three senders are sending different kinds of messages to a receiver, but notice the receiver doesn't freak out or have to lock down its state in order to deal with those three messages because each actor, and depending on implementation, each actor has a mailbox, and the mailbox acts as a queue for the receiver, and the queue itself can be implemented lock-free in that messages that are being delivered are enqueued lock-free, and then the receiver processes those messages one at a time, which means that internally the actor does not have to lock its own state in order to prevent some sort of volatile state collision inside. Actors have the ability to prepare for their next message, so the receiver of incarnation 1 or of behavior 1 receives one kind of message as the step 1, and when it receives that message, it becomes another kind of message listener by essentially replacing its message handler at runtime, and therefore when it receives message from sender 2, this message can be interpreted in the behavior of the newly formed actor receive block. Actors are not used alone. Actors come in systems. And you'll typically see an actor system that has a hierarchical structure, and this lends itself to supervision control and also allows the actor system to scale, and for you to be able to reason about all of the actors that may be running in an actor system. And actor concurrency can be denoted by this kind of diagram, and notice that if you can see that there are multiple step 2s and multiple step 3s, that's not a mistake on the diagram. Those are actual concurrent operations that are happening because of simultaneous message sending and delivery. So for example, step 1 is a client sending a message to a router. When the router receives that message, it takes 2 steps. It sets a timeout using a scheduler for itself, and when that timeout would occur, if it occurs before the other part of the use case finishes, then step 3 will send a timeout message to the router actor. But notice that simultaneously with the timeout even being set, the actor is also sending a message to a receiver actor in a simultaneous step 2, and then there's a race condition. Will the timeout message be delivered before the receiver takes step 3 and sends a message back to the original router? If the timeout message is received first, then the timeout occurs. Otherwise, if the receiver sends its message before the timeout message enters the mailbox of the router, then that's what will be delivered. And so step 4, going back to the original client, will either be a succeeded kind of message or a timed out message. So how many actors can we have in an actor system? Do you think 50 plus is a good number? You think 100 maybe? You think 1 million plus? Well, you would all be correct. Actually, many millions of actors are not unusual depending on the size of perhaps the VM that the actors are running in. So you can scale actor systems, and remember that because you are running potentially millions of actors, the actors are all getting a slice of each core or hyperthread that's available at any given time, and so it's shared. And a typical scheduling policy for actors is to allow one actor to process one message, and then a thread is handed off to another actor. So, but all of this threading is in the background. You don't have to worry about it. And therefore, it makes actors far easier to reason about than typical multi-threaded code. All right, so here's another compelling reason that I think you should consider for using actor model is when you think of a typical n-tier architecture, this is, sort of what you face. If we're using the ports and adapters architecture, what some call the onion architecture or hexagonal or hexagonal architecture, you typically have a set of adapters at an infrastructure layer on the outside, and then you have the inside, which is the application services, and the application services manage tasks for use cases or user stories, manage transactions, security, and so forth. And ultimately, using domain-driven design, we want to hand the heavy lifting of the business operations off to the domain model, which is at the heart of the software. Okay, not so bad, but when you consider the actual components in each of these layers and the potential of concerns that each layer has to deal with, I think that this is, in many cases, a very complex system. I refer to it as the complexity stack. Now, it's not that any one of us can't learn this, and when we go into a new, say, project opportunity, it may take us a number of weeks or even a junior or mid-level developer a number of months to wrap their mind around the complexity of the architecture, but they can succeed. But what about using the actor model? Because of some advantages to actors, using the actor model, I think, delivers what I call the simplicity stack. You have the user interface, and assuming that we have a user interface at all, but in a given bounded context, let's say we don't even have a user interface, maybe the user interface is actually a set of service endpoints of some kind. But those service endpoints can then just directly send messages to an actor in the domain model, and that's one kind of message, and then the domain model can emit another kind of message. And it becomes very, very simple to reason about these systems, and this is something that I think junior and mid-level developers can wrap their mind around right away, and because there isn't the cognitive overload of dealing with multi-threading, then reasoning about actors is quite simple. Okay, so where do actors and domain-driven design sort of meet together? What are the advantages? Well, I want to highlight two important features of the original ideas behind object-oriented programming. Again, Alan Kay made these statements. The actor model retained more of what I thought were the good features of the object idea. So Alan Kay is a fan of the actor model. And of course, the actor model was inspired by Alan Kay's work on Smalltalk. And, but it's interesting that Alan Kay says that in essence, you know, wow, this is the idea that I really originally had. I don't know why Smalltalk as a core platform didn't take on the actor model in public editions. Maybe it was because processors in the day weren't really ready for that. But again, Alan Kay says focus on the messaging. The messaging between actors or objects is the big idea. It's the important thing. Therefore, another question that I was asked last year is, well, you know, depending on the implementation of the actor model, there's a possibility that some actors actually take on a responsibility for persisting their events, such as when there's an event-sourced actor, the actor can take on the responsibility of persisting events. And so the question was asked, isn't this a sort of violation of the ideas behind good object-oriented design and single responsibility principle? Well, maybe, but think of this in another way. If the messaging between objects is the big idea, and Alan Kay, essentially says, don't give so much attention to the inner implementation of the object, because it's really the message exchange that's the important thing, then what the actor does is its own business. And besides the fact that, as I'll show you more clearly in a moment, the entity actor that is event-sourced, or the aggregate actor that is event-sourced, is not actually responsible for its own persistence, okay? So there is more to that story, and I'll explain that. So where I think actors play a big part in domain-driven design itself, even besides the fact that the future of computing seems to be leaning toward needing the actor model in software systems, I think that dealing with the rapid production of new business ideas, the rapid production of new markets and so forth in business puts a lot of stress on development organizations, on software development organizations. And trying to keep up and respond to new business direction in a rapid fashion is a huge challenge. I hear it all the time. So DDD, I think, enables us to crunch the knowledge, do the knowledge crunching that's necessary, and have good throughput on all of the information that's necessary and collaboration. But I think actors and messaging enables for the rapid implementation of those new requirements. And it also allows for clear understanding. Now, Mel Conway this morning talked about domain experts not being able to potentially reason about the software. I think that there is a means with the actor model to help domain experts to more clearly understand and participate in the software design and development steps that are necessary with DDD. So the essence of domain-driven design is developing a ubiquitous language inside a bounded context. Okay, so obviously everything that I'm discussing here is framed within the discussion of a bounded context. And a ubiquitous language can be created with an object model. And when Eric wrote his seminal work on domain-driven design, he said that object-oriented programming is a good way to express a domain model, and I agree with that. So if we are working on and focusing on a ubiquitous language, how do we implement a ubiquitous language with actors and messaging? Does it work well? Here's an example, and this example is taken from my books, but those books were talking about object-oriented. This is showing the same kind of use cases, but as expressed through actors, all right? So we have two actors here, and notice that I'm drawing actors as circles. That's so that they aren't confused with objects, okay? And there's some precedence for this that Gul Agha wrote a book in the mid-'80s, which was his PhD dissertation on the actor model, and he used circular representations for actors then, and it's kind of caught on a little bit, so I think it's a good way to show actors. So we have a product actor and we have a backlog actor. This is in the bounded context of an agile project management application that helps Scrum-based teams manage their products, their Scrum products, and the development of those products and the release of the software. So we have a product that takes a command message and it emits an event message. We have a backlog item that takes as a message a command and emits a message which is an event. There may be more to the ubiquitous language than this, but in terms of expressing the high level of our ubiquitous language through actors, this is pretty much it, okay? And again, I'll get into some implementation details in a moment where you have the opportunity to leverage other forms of development inside the actor, but essentially, this is what I'm referring to as expressing your ubiquitous language. And domain experts can understand this. They can understand that a command is being sent to an actor, and when the actor receives that command, it's carrying out that command, and as a response to that command, the actor is emitting a domain event, and that domain event expressively records the fact of what happened within the actor. So the domain objects are actors, and the messages that they process are generally command messages, and the messages that they emit are generally event messages. So how do we come up with a model like this? Event storming is a good way to do that. Now, we can event storm at the big picture level, and that's a very good thing, and we should, at a minimum, start out there. But we can also take smaller sections of an event-stormed model, which may actually span many bounded contexts. But if we start to focus on a core domain within that large system that we've event-stormed, then we can actually go down to a design level and use event storming to represent actors and the command messages and event messages. We actually start out modeling the events first, then we move on to the commands that cause them, which can sometimes make us think of other events that need to be handled, and then finally we model the actors that maintain the state of the system. I'm sorry that I wasn't able to find round sticky notes for the actors. That was really hard to come by, so I've just had to use rectangles. Okay, so when we boil our ubiquitous language down, what we're really talking about here are aggregates that are largely involved in carrying out the use cases of the system. We have a sender, which is most likely some service endpoint at a boundary level or a UI controller, and they are dispatching command messages directly to aggregates in the model, and the command messages adhere to the ubiquitous language. The actors that are aggregates adhere to the ubiquitous language. The domain events adhere to the ubiquitous language. But notice when the events are ultimately persisted to a journal, it's not that the actors themselves are involved in persistence. It's actually that the actors are sending or emitting events to a journal that actually they don't even know about. It's abstracted away, and that journal takes care of asynchronously persisting the events and asynchronously informing the aggregate that the events were persisted, and in that case allows the actor to know that it can then transition its state to reflect the fact that these events are golden at that point in time. So the aggregates support transactional consistency on their own. You don't need another component to manage transactions, and that's why I can say that the senders of these command messages could be the user interface. We can actually get rid of an entire layer because the actor stands in a good position to manage its own use case. So aggregate implementation as actors, how do we do that? So actually within the aggregate itself, I like to represent the state of the aggregate as an immutable object, or in functional programming, an immutable record. And so actually there's a way both through object-oriented if you're using Scala, for example, and if you're using a more pure functional language such as Erlang or Elixir, that you can represent the state changing through an immutable object. And if you're going to attend my 2-hour workshop tomorrow, you'll see how that can actually be accomplished. How do you transition and replace the state of a command? That will also be explained. And then how do we emit corresponding factual events of what happened, and how are they persisted? We'll talk about that. And so ultimately what happens is, as commands are happening in each bounded context and events are being emitted and put into a bounded context event journal, ultimately the domain events can flow to a central message bus, and that central message bus can deliver events to other interested parties within, or other bounded contexts within the system that you're developing. So it fits well with the idea of breaking up different languages into different bounded contexts. So tomorrow I'm going to speak or teach a workshop on using the actor model with DDD and Akka. So you can, if you want to attend that, you can use Scala. And I highly recommend using Scala and not Java. The Akka team is working on some improvements to the Java API, but at this point in time, I think it might actually not be a good experience to use the Java API. If you prefer C#, you can use C# with Akka.NET, which is a port of the JVM version of Akka 2.NET. You could use F#, but I don't know F#. Maybe we could get Jeremy to attend and he could explain F# to you. Or you can use Erlang or Elixir, which both support the actor model in a pure functional environment. I only ask that because it's only a 2-hour workshop that you carefully consider using a language that you understand, because I won't be able to teach you how to program in any of these languages in 2 hours and still give attention to, you know, the goals of this workshop. So I hope that you're able to attend, and that's all that I have on DDD, or the language of actors, and I hope some of you are able to join me tomorrow.
Okay, so Akka.NET has support of receive async. So basically, what's your take on that one? would you recommend using async?
Akka.net
Yeah.
supports. Can you? Actually, I'm familiar with the core actor capabilities. Are you talking about persist async or?
No, I'm talking about receive method, so that processes your inbox, and there is.
So you can actually process multiple messages at one time simultaneously.
Yeah, there are.
Well, that I mean.
Pipe 2 pattern
That's
as well.
yeah. That's really not the actor model, though. I think so. I don't necessarily comment on that. I wasn't even familiar with that. But what I'm proposing here is the use of pure actor model. So I would say that is really not actor model, although it could be useful.
I have a question about when you would recommend using this approach for a system. The reason why I'm asking is I've worked in embedded software engineering where you use these kind of systems a lot, and to me they always made sense there. But since working in web environments more, I never really felt that it fits. So what would you say, when does it make sense to use that approach and when not?
I've used it in web environments, but are you talking about a web application or just for a web server?
Yeah, for a web application, for example.
Yeah, I've used it with web application. If you're modeling a ubiquitous language and if your actors can represent the aggregates in your system, then I think that's a good place to use them. Now, typically actors haven't been used from the far past for dealing with things like aggregates, but they can be used that way. And I didn't touch on the bigger picture of process managers and things like that, but actors can be used for domain logic, in your entire application. So, maybe what we could do is talk more about that after this, and I could get a better idea of the things that you're thinking about, but it depends on maybe your goals. So let's talk about that a bit later.
Maybe stand up, then people can see where to throw. If you have a question. Oh, there, sorry.
Hi. I just wanted to ask about, you had these two slides, the complexity stack and the simplicity stack. Mm-hmm. And the complexity stack was taking over so many concerns, and I didn't quite get how all of these concerns map into the simpler version, like security, data validation, all this stuff. These responsibilities don't go away. How does it map?
Yeah, well, so security, I've typically handled that at like REST endpoints, so that can get folded in, and security then falls away from the application layer. And when you don't need a process manager, then essentially the idea of an application service just sort of melts away. If you do need to manage a multi-step process, you can use an actor to model that, and it goes in front of the aggregates. But I think that this is accurate, though. I mean, I think that this view is really accurate, and what I'm not showing here is that event journal that's taking the events. Now, you have to decide also, if you're going to use this approach, are you going to use event sourcing? I'm talking about event sourcing. That may not be a good match for you, but you can also persist the serialized state of the actor as well without using event sourcing. But events are very useful whether or not you're using event sourcing. So you have to think about that. And that's a more or less popular statement that I just made.
In a typical, at least object-oriented paradigm, an aggregate encapsulates a collection with or communication with entities and value objects. Mm-hmm. So there is still a messaging passing between a root entity and sub entities, right? But in this model, using the actor model, how do you manage the messaging passing between these?
I think I know what you're saying, and I have seen the use of multiple actors to model a single aggregate, as in child actors will play the part of an entity, I don't like it. So I model all the entities and all the value objects within a single aggregate actor, and typically I'm able to do that in an immutable way, so a functional way, and only one piece of state in the entire cluster is mutable, and that is the variable that holds the reference, and I'm talking about Scala. If you're using Erlang or Elixir, it's purely functional, purely immutable. And again, tomorrow I'll explain how that's managed.